All right, so today we're gonna continue on with the method of joints. So now that we've seen the gone over equilibrium, so we can use that, apply that to analyze the system. So the method of joints is used to analyze loads in a frame or in a truss system. And the way that I'll introduce the method of joints to you is going through a basic example of a truss and analyzing it to see how you can apply the method of joints to actually do the analysis. Yeah. Joints. So we're going to start with a basic example of a truss. So it's just going to be a simple system with just 3 members and 3 joints. We're going to have joints A, B, and C. Joint A we're going to have as a fixed hinge joint. Joint B we're going to have as a roller joint. Joint C is just going to be a pin joint, but we're going to have an applied external force here. And just to give us, so we can do some numbers later on, we'll have member AB be 10 meters long, and joint C is positioned above the midpoint of the beam. So it's 5. And then the height of the beam will also be 5 meters. All right. So our goal is going to be to determine all of the member forces and all of the reaction forces. So first, let's go through the system and determine what are the member forces and the reaction forces that we don't know yet. So the members that we have are simply AB along the bottom, and then the two diagonal ones, which are AC and BC. And so there's basically just a force within each of these members. So our member forces are FAB, FAC, and FBC. And the other forces that we have are our reaction forces. We only have two joints that have reaction forces, A and B. A fixed hinge joint has a reaction force in both the X and Y direction. So we have FAX and FAY. And we also have the roller joint at joint B, and roller joints have just one reaction in the Y direction. So we have FBY. There can be no applied force in the X direction at a roller joint. So here we have 3 member forces and 3 reaction forces. So total unknown forces is 6. So this means that we will need to generate at least 6 additional equations so that we can actually determine what all of these unknowns are. So, and we know that we can do this because we have 3 joints, and what we'll do with each joint is do the summation. We know that we can do the summation of all the forces in the X direction, and all of the summation of all the forces in the Y direction at each joint. So we can have at least 2 equations per joint, which will give us 6 equations. And you see here that these are the same. So what that tells us is that this system is statically determinate. And what that means, that basically just means that we can't actually determine what all the forces are in the static situation. So this, mathematically what this is telling us is that the number of unknown forces is less than or equal to the number of equations that we can generate. All right. Any questions on this so far?
So that is less or equal to? Or does that matter?
Right. So if we have we have the case where it's equal to, but if we only had 5 unknown forces and we could generate 6 equations, we would still be able to determine what all 5 of these forces are. So that's fine. So this would be like an overdefined.
So will there be a solution that can satisfy all the?
Yes. The inverse of this would be if you had, say, 7 unknown forces and only 6 equations. That would be a statically indeterminate system.
So will there be an over-determinate system so that you will not find a solution that is perfectly satisfying all this equation?
No, as long as you have more equal or more or fewer unknowns, you'll be able to find a solution that satisfies. Yeah, we'll actually come back to this later. We'll see that you can have 0 force members, which is where you get into the having more equations than unknowns.
Excuse me. So there are 3 joints and 2 times 2 equation. Where does the 2 equation comes from?
Okay, so those are you'll see that in a second, but basically we know that we can do a summation of all the forces in the x direction and a summation of all the forces in the y direction at each joint.
Okay.
Yeah. Okay. So the first thing to do in the method of joints is to look at the system as a whole. So we'll look at only the external forces. So we'll draw the overall system again, looking at just the external forces. So the external forces are our applied force, our reaction force. Remember at joint B, we have only the reaction force only in the y direction, not in the x direction. But at joint A, we had a reaction force in x and y. All right. So we have to remember that the two of the equations that we can use are the summation of all the forces in x and the summation of the forces in y. Let's start with let's move over here. Let's start with the summation of forces in x. And since this is a static system that's in equilibrium, we know that the summation of all these forces has to be equal to 0. This is the definition that we can rely on. And we see here that there's actually only one force in the x direction. So FAX is going to be equal to 0. If we do the summation of the forces in y, we see that we have F, which we have to have negative since it's pointed pointed downward, plus the 2 reaction forces, which again is going to be equal to 0. But here we see that we know what F is. We know that it's an implied force. We're going to assume, for the sake of the problem, that F is going to be equal to 10 kilonewtons. But we don't know what FAY or FBY are. So we need additional information. So what we can do is take a moment around joint A. We know that since this is just a pin joint, there can be no applied forces, no torques around this joint. So this moment has to be equal to 0. So if we look at the moment, we have our applied force, which is 5 meters away, and we have our reaction force at By, which is 10 meters away. So, and this is going to be equal to 0. We know that our applied force is 10 kilonewtons, 5 meters plus y. So you can see here that Fby, our reaction force in the y direction at B, is going to be equal to 5 kilonewtons. All right? Any questions on how we got there? All right. So now we can use this solution, plug it back into the summation of our forces in the y direction to solve for our reaction force at A in the y direction. So we have negative 10 plus Fay plus 5 is equal to 0. So our reaction force at A will also be equal to 5. So let's start a little chart where we can catalog all of our results. So we have the things that we want to find are Fax, Fay, Fby, Fab, Fac, and Fbc. All right, so we're halfway done. The next step will be looking at the free body diagram for joint A. So the way that the method of joints works is that you basically walk through the entire system, first doing this overall equilibrium, and then looking at each joint in the system. So if we draw our free body diagram for joint A, we have our joint, we have our reaction forces, and our member forces. So you'll see, remember here that Fax is 0, so we're actually just going to eliminate this just to make it a little bit easier for us. And you'll see here that we know Fay, but we don't know Fab or Fac. And I have assumed that that the beams are all in tension. It doesn't really matter which way, if you assume if they're in tension or compression, as long as you're consistent with your assumption throughout the problem. And what you'll find is that it all works out in the math, and that if you end up with a negative tension, your beam will really be in compression. So just like before, what we're going to do is a summation of all the forces in X and a summation of all the forces in Y. So let's start with X, which we know has to be equal to 0. So here we have Fab plus Fac times the cosine of our angle. And we know that our angle is going to be 45 degrees if you look at the initial setup. So this is 5. We said the height was 5. So this is just a 45, 45, 90 triangle. So we know that our angle here is going to be 45 degrees. If we do the summation of the forces in Y, which we know would be equal to 0, we have our reaction force at A in the Y direction, and we have the Y component of Fac. So if we look at the summation in X, we don't know what Fab is, we don't know what Fac is, so that one's not useful yet. But here, we know Fay, we don't know Fac, but we can use this to solve for Fac. So the member force in member AC. So we have Fac is going to be equal to negative reaction force at A divided by the sine of 45. And we know that the sine of 45 is equal to the cosine of 45, which is equal to 1 over the square root of 2. So this is going, since we know Fay is 5, this is going to be negative 5 times the square root of 2. All right? We can use this, plug back into our summation in x to solve for FAB. So we have FAB is going to be equal to negative FAC times the cosine of 45. Plug this in, make sure you carry the negatives, square root of 2 times 1 over the square root of 2. Square roots of 2 cancel, the negatives cancel, so we find that FAB is going to be equal to 5. Remember, the units is kilonewtons. All right, so let's put these into our chart. We have FAB is equal to 5. Put it in our units. FAC we said was negative 5 times the square root of 2 kilonewtons. And now we're done with joint A. So we're going to move on now to joint C. So joint C, remember we had our applied force, and then we had our two member forces. So we have FAC and FBC. These are our applied force. And we can actually, we noticed that one of the initial assumptions that we made, that the beams were in tension, was wrong just by looking at this free body diagram. We know that the system is going to be have no net force, but if we look at all of these forces, at all of this, all of the forces are in the downward direction. So we know that our summation can't be 0. But we've already seen that at least FAC is actually negative. So, and we can assume that since this is a fairly simple system, we know that FBC will actually also be negative. But again, it's important to keep your assumptions that you've made in the very beginning consistent throughout the entire analysis, and then go back and revise your assumptions at the end. One thing you can potentially do is actually go back and redraw the entire system. So you could draw joint C like this. You still have your downward applied force, and you can reverse the direction of FAC and FBC. But here, what you have to do is relabel FAC as being positive. So it'd be 5 times the square root of 2 instead of negative. And this is fairly simple for this example that we're doing now. But think about if you had a real trust that had thousands of members. That it becomes much more difficult to actually go back and redraw every joint every time that every time that you find that you made an incorrect assumption. So if you just leave it in the initial orientation, it's fine, and just it'll work out in the math. So we're going to leave it as it was in the beginning. Now, again, we're going to, just like before, do our summation of forces in x and y. We'll start with x. We have negative FAC times the cosine of 45 plus FBC times cosine of 45, which we know has to be 0. Again, this negative comes from the fact that the x component of the member of forces in AC will be to the left. Our summation in y, we have our applied force, and again, our member forces are all downward, so we have negatives again. So sine 45 minus BC. That's the sine of 45 will be equal to 0. All right. So first, let's look at the summation in X. Since we already know FAC, we want to find FBC. So here we can actually just solve. You can see that the cosines of 45 cancel. So FAC is going to be just equal to FBC, which is equal to negative 5 times the square root of 2. And you come back over here. And we see now that we actually have all of the parameters that we were looking for. We've solved for all of our reactive forces. We've solved for all of our member forces. And the reason that we were able to do that without using all of the summations, without using this last one, and looking at joint P, is that we use that moment equation in the beginning. So that allowed us to not have to use all the equations, but that's not something you can always do. Well, yeah. So, but what we can do, we can still use this last equation that we've already written out as a check for our numbers. So we know that our applied force was 10 kilonewtons. FAC was minus 5 times the square root of 2. Sine of 45 is 1 over the square root of 2. FBC was negative 5 times the square root of 2. 1 over the square root of 2 is equal to 0. All the square roots of 2 cancel. We get negative 10. We get double negatives. So we have plus 5 is equal to 0. 0 equals 0. So here we see that all of our numbers check out. And so this was a very simple example, but the thing to keep in mind is that this general process is applicable for any sort of truss system, regardless of how many actual joints you have. And yeah, any questions on that?
So under what condition do we have to apply the moment into our equation?
Well, so we didn't have to do that in this one.
So,
it just made it easier for us. So
okay.
you can take it on a sort of a case by case thing. If we hadn't done that, we wouldn't have been able to solve for the reaction forces right away. We would have had to wait until we had generated
every member.
Every member. So it just that's all. It just allowed us to simplify the number of unknowns that we had to carry throughout the entire analysis.
Okay.
So it'll depend on the sort of situation. There'll be some times when the number of of moment equations that you have will just be too many to want to do.
Yeah.
So, yeah. All right. And the next next class when we come back, we'll start looking at what's called the method of sections. And that instead of here where we only looked at basically the joints throughout the truss, the method of sections allows you to look at just specific areas within a truss, and that can be useful in a large system where you have many joints and you're only interested in the forces in a specific area. So it allows you to reduce some of the analysis that is required.